An iron toroid has a mean path length of 1 meters and a cross-sectional area of 4 centimeters square. 1600 turns are wound on the toroid and a current of 1 ampere is passed through the winding. The relative permeability of iron is 1500. Estimate the flux under these conditions. And now an air gap of length 0.5 centimeters is cut in the ring. Estimate the flux under these conditions. And in part C, calculate the current needed to return the flux in the cut toroid to the value in the uncut toroid. Okay, so here is our toroid. It has an inner radius R1, outer radius R2. The mean path length will be basically determined by finding the average radial distance from the center and the circumference of the circle defined by this average radius. The cross-sectional area A is the cross-sectional area of the toroid, so the cross-section is basically here circular. It's filled with iron which has relative permeability mu sub r, which is 1500, and there are 1600 turns, and there's 1 amps current flowing through this winding. Okay, so let's start in part A by determining the noting the findings we have here. 2 pi times r1 plus r2 divided by 2. This is our mean path length. This is pi times r1 plus r2, inner and outer radii, and that is given as 1 meters. The cross-sectional area A, it was given as 4 centimeters square. So if we're going to do an SI calculation, we should convert this to meters square. This will be 4 times 10 to minus 4 meter square. The relative permeability is 1500. Now what we will do is we will use magnetic circuit analysis. So using magnetic circuit analysis, we have to find the magnetomotive force. The magnetomotive force, which is the analogous quantity to electromotive force. This is MMF, the other one was EMF. It is the closed path integral H dot dl, magnetic field dot product with the displacement on the path. So this is equal to the number of turns n times the current I, which is the flux that flows through the circuit multiplied by reluctance R. So if we recall our analysis of magnetic circuits, the analogy was such that the flux phi that flows in the magnetic circuit is analogous to I, the current in an electrical circuit, and the reluctance R was analogous to R resistance in an electrical circuit. So this is what we recall from the lecture. All right, now we can calculate the reluctance of the toroid. The reluctance R is the mean path length L divided by the permeability mu r, mu 0, and cross-sectional area. So this is basically L mean path length divided by mu permeability times area. So if we substitute the numbers here, we have a mean path length of 1 meters. Relative permeability is 1500. Mu 0 is 4 pi 10 to minus 7 Henry per meter. and we have area 4 times 10 to minus 4 meter square. So this is equal to 1.3 times 10 to 6 ampere turns per Weber. So the flux is found by the magnetomotive force here. It's Ni divided by the reluctance. So this is Ni divided by the reluctance of the toroid, and this is 1600 turns times 1 ampere divided by the reluctance we have calculated 1.3 times 10 to 6, and this gives us 1.2 times 10 to minus 3 Webers. So that's the flux in the toroid. Now in part B, we are introducing an air gap, and with the air gap here, so we will have the toroid basically now has this air gap here. All right. So this is now air and this is iron. In this case, we have to consider the reluctance of the air as well. So that part will have the path length in air, L air, divided by permeability in air, multiplied by the cross-sectional area. You can see that the cross-sectional area is the same. So it's the cross-sectional area of the toroid. So this is basically the same area A. So this is going to give us the gap was 0.5 centimeters. So it's 0.5 10 to minus 2 meters divided by permeability in free space is approximately the permeability in air, 4 pi 10 to minus 7. Cross-sectional area did not change, 4 times 10 to minus 4 meter square. So this gives us a reluctance of 9.9 times 10 to 6 ampere turns per Weber. Now we have a new path length in the iron. What is our new path length? Because we have consumed 0.5 centimeters for air. So this is basically 0.995 meters. This is our new path length. So we can calculate the reluctance of the toroid now, the modified reluctance, using the new path length. It's the path length in the toroid, L toroid, divided by mu sub r, mu 0, a cross-sectional area A. The new path length is 0.995 meters divided by 1500 times 4 pi 10 to minus 7 times 4 10 to minus 4 meters squared. This was our cross-sectional area, and this gives us a reluctance of 1.32 times 10 to minus 6 ampere turns per Weber. So we can now calculate the total reluctance, because this is a magnetic circuit in series. We have the reluctances adding up, contribution from air and contribution from the toroid, the iron part. This gives us 1.12 times 10 to 7 ampere turns per Weber. Okay, so ampere turns per Weber. The flux is the magnetomotive force, number of turns multiplied by the current I, divided by the total reluctance. This is 1600 windings, 1 ampere current, divided by the total reluctance, 1.12 times 10 to 7. This gives us 1.43 times 10 to minus 4 Webers. So that is the result in part B. Now in part C, we want to change the current so that we obtain the same flux. You can see that the flux has decreased. It was 1.2 10 to minus 3. It's now 1.4 10 to minus 4. The flux is going to be equal to the flux in the uncut toroid, which was 1.2 times 10 to minus 3. And how do I obtain that? If I change the current so that the magnetomotive force changes, 1600 I divided by 1.12 times 10 to 7, the total reluctance, this gives me a current I 8.4 amperes needed. So I have to get almost 10 times the current in order to get the same flux. Well, approximately 10 times. Okay, so we're using magnetic circuit analysis to calculate the flux in a toroid that is made up of iron. The iron permeability is relative permeability is 1500. We have capital N turns, 1600, cross-sectional area 4 centimeters squares, and the mean path length of 1 meters. Now in this toroid, if you use the right-hand rule, you can follow that the current is flowing like this. So it's basically on each winding pointing towards the center, as you can see here. So by using the right-hand rule, you can see that the magnetic field produced by this current is going to be always perpendicular to the current, and it's found by wrapping your forefingers in the direction of the current and looking at the direction in which your thumb points. So for each of these, we have a contribution to the magnetic field. Let's make this smaller. So we have the magnetic field H here. So it's going to be perpendicular to the current in each winding. So this will be going in this circle like that. So we will see that this will basically have the dot product H dot dl along this path. So we are basically going in this circle that is defined by the mean radius r bar. So that r bar is r1 plus r2. So the path length here, L, is basically the mean path length, that is the circumference of this circle. So that is pi r1 plus r2, that's 1 meters. Cross-sectional area and mu r are given. Now integral, closed path integral h dot dl. For each dl here we have, since the dl is parallel to the local magnetic field, h dot dl becomes h times L. And that magnetic field H is found by using Ampere's law, if you remember, and it is N times I for H, or mu 0 N times I for magnetic induction B. So H dot dl is basically going to give us the magnetic field multiplied by the path length L here. So this is going to be equal to N times I, that's phi flux multiplied by reluctance. So this is going to be analogous to the current. Flux is analogous to the current, and reluctance is analogous to the resistance. So we have reluctance given by L divided by mu A. So we need to calculate this for iron. Our path length is 1 meter, so 1 meter divided by 1500 times 4 pi 10 to minus 7 mu 0 permeability of free space and cross-sectional area gives us the reluctance, and the flux is the magnetomotive force Ni divided by the reluctance, 1.2 10 to minus 3 Webers. Now we're changing this path length. We have a portion of it in air, so this is going to be the portion in the air. So we have L air plus we have the portion that is inside the toroid, and that will be L toroid. This is modified, as you can see. So we have 0.995 meters in the iron and 0.5 centimeters in air. So the reluctance of the air is the path length in air divided by mu air times A, 9.910 to 6, and the reluctance in the toroid used to be 1.310 to 6 ampere turns per Weber. Now it is 1.32 10 to 6 ampere turns per Weber. Okay, so there's a minus sign, I corrected. So the total reluctance is going to be 1.12 10 to 7 ampere turns per Weber. So the flux is a magnetomotive force Ni divided by the total reluctance. I'm assuming no leakage here, so there will be some loss of flux due to the leakage in the air, but we're assuming that that is negligible. So this is going to give us 1.43 10 to minus 4 Webers. In order to get this, so it's almost 10 times less than the value we obtained in the straight toroid with no air gap. We have to introduce a larger current, which is found by calculating the flux with the new current 1600 I divided by the total reluctance, and we see that we need to increase the current almost an order of magnitude to see the same effect. So in order to get the same flux flowing through the air portion.